the pale blue dot. This image, which has become a symbol of our planet's fragility and beauty, was taken from more than 6 billion kilometers away. It shows Earth as a tiny speck suspended in a ray of sunlight, almost impossible to see against the cosmic expanse. Simple, yet powerful, it makes us reconsider our place in the universe. This historic photograph was snapped by the Voyager 1 spacecraft in 1990 at the special request of astronomer and writer Carl Sagan. It's part of a set of solar system snapshots known as the Family Portrait. Voyager 1 and 2 are much more than just machines. They stand as silent witnesses to our quest for knowledge, our knack for innovation, and our unending curiosity. Through their discoveries, these probes have broken barriers, defied expectations, and forever changed how we understand the cosmos. In this video, you'll learn the full story of these spacecraft, from their origins to their greatest achievements, and find out why they're considered the most distant and remarkable objects ever built by humankind. Will they ever encounter an alien civilization? Welcome to humanity's greatest journey yet, toward the infinite horizon. The Voyager's story actually began long before their 1977 launches. They're direct descendants of an earlier NASA effort, the Mariner program. Mariner was NASA's first interplanetary exploration project, designed to study the inner planets, Venus, Mars, and Mercury. Over the course of the program, 5 distinct missions flew a total of 10 probes. 7 succeeded, while 3 failed. The first Mariner mission launched in 1962, 7 years before the first humans stepped onto the Moon. Buoyed by those earlier successes, NASA decided to take a bolder leap. In 1972, planning began for a new program that would eventually become the Voyager mission. The driving idea was a rare, once-in-a-lifetime alignment of the solar system's 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, perfectly positioned so that, with a sequence of gravitational slingshots, a spacecraft could hop from one to the next, virtually fuel-free. It was a unique opportunity. This alignment only happens about once every 175 years. Exploiting it would slash interplanetary travel times from decades to just a few years. To make it happen, NASA designed 2 identical probes. At first, they were called Mariner 11 and Mariner 12, but as their mission grew far beyond the original Mariners, they were renamed Mariner Jupiter Saturn. Still, it wasn't until March 1977, just months before launch, that the program got its final name, Voyager. The 2 spacecraft became Voyager 1 and Voyager 2. While they were being built, Carl Sagan, already a respected scientist and science communicator, proposed a bold, inspiring idea: include a record of humanity aboard each ship. That's how the golden records were born. These are copper discs plated in gold, meant as time capsules and messages for any intelligent life that might one day come across them. Sagan chaired the committee that chose the record's contents. The goal was to create a broad portrait of life on Earth. Each disc holds 115 images ranging from human anatomy to cityscapes, landscapes, and animals. It also carries ambient sounds, wind, rain, a human heartbeat, and 31 pieces of music from cultures around the globe, plus greetings in 55 different languages. But the golden records go even further. They include basic scientific information about physics, math, and biology, along with maps showing Earth's location in the solar system and our galaxy. While the odds of an extraterrestrial civilization finding them are vanishingly small, these records stand as a symbolic reminder of our wish to reach out into the unknown. As Carl Sagan put it, the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Finally, on August 20th, 1977, Voyager 2 lifted off, followed by Voyager 1 on September 5th of the same year. The order might seem backward. Voyager 1 launched second, but its trajectory was faster, allowing it to overtake its twin and reach the initial targets first. The launch dates weren't chosen by chance. That summer, the four gas giants were aligned in just the right way, an incredibly rare event occurring once every 175 years. Using each planet's gravity as a slingshot was key to the mission's success, cutting both travel time and fuel needs dramatically. Voyager 2's path was plotted to visit Uranus and Neptune after Jupiter and Saturn, while Voyager 1 took a different route focused on Jupiter and Saturn, and especially their most prominent moons, like Io and Titan. That trajectory meant Voyager 1 wouldn't visit the outer planets or Pluto, which was still counted as the solar system's ninth planet at the time. The plan was straightforward: study Jupiter and Saturn, then use Jupiter's gravity to boost the craft onto Saturn. The launch vehicles provided just enough speed to reach Jupiter. From there, the probes would be flung outward on their unprecedented interplanetary adventure. In January 1979, Voyager 1 reached its first major milestone, Jupiter. That's when the mission truly began to show its power. As the probe closed in on the giant planet, it started taking photos and gathering data that revealed secrets never seen before. Its closest approach, on March 5th, brought it within just 216,000 miles of Jupiter, a tiny distance next to a world the size of the gas giant. During that flyby, Voyager 1 captured the highest resolution images yet of Jupiter's upper atmosphere, its colorful bands, and especially the Great Red Spot, a storm larger than Earth that's raged for centuries. Those images transformed our understanding of Jovian weather and dynamics, showing a world in constant, violent motion. Voyager 1 also made a discovery that stunned scientists: active volcanism beyond Earth. The probe observed eruptions on Io, one of Jupiter's moons, the first time humans had seen a volcano erupt on another body. With its sulfur-stained surface and explosive plumes, Io revealed itself as a hyperactive world, overturning the idea that moons were cold, inert rocks. In July 1979, Voyager 2 also flew past Jupiter, though not as close as its sister, passing at about 570,000 kilometers. Even so, its data filled in key details and added new perspectives on the Jovian system. Together, the Voyagers revolutionized our knowledge of Jupiter and its moons. They studied the four Galilean satellites, Io, Europa, Ganymede, and Callisto, that Galileo had spotted in 1610. Their observations suggested Europa likely harbors a subsurface ocean beneath its icy crust, a place where life might exist. On Io, they documented 9 separate eruptions, some shooting material hundreds of kilometers into space. They also discovered Jupiter's faint ring system, previously unknown, and found 3 new moons: Adrastea, Metis, and Thebe. These were the first Jovian satellites spotted by spacecraft. Beyond images, the Voyagers measured Jupiter's magnetic field and radiation belts, data essential to understanding the planet's inner workings. After gathering all that information, the probes used Jupiter's gravity to catapult themselves towards Saturn. Voyager 1 made its closest pass by Saturn on November 12, 1980, coming within 124,000 kilometers of the cloud tops. Voyager 2 followed several months later, in 1981. Saturn, with its mesmerizing rings, proved even more complex than scientists had imagined. The Voyagers found storms with winds over 4,800 kilometers per hour, among the most violent ever recorded. Their images revealed fine structures within the rings, gaps, waves, and divisions no one had seen before. 3 more natural satellites were discovered: Atlas, Prometheus, and Pandora. The probe's instruments also studied in depth the planet's atmosphere and its largest moon, Titan. Voyager 1 was specially steered in for a closer approach to Titan, thanks to Pioneer 11's earlier discovery of a dense atmosphere around that moon. The decision to send Voyager 1 toward Titan was strategic. Scientists had to choose between continuing on to Uranus and Neptune or seizing the unique chance to study this mysterious moon more closely. They opted for Titan, given the unprecedented scientific value of examining its thick, complex atmosphere, something never before seen on a moon. That maneuver had consequences. The Titan flyby threw Voyager 1 out of the planetary plane, sending it off the ecliptic, the orbital plane of the solar system's major bodies. In other words, it could no longer visit the outer planets. However, thanks to that decision, Voyager 1 detected hydrocarbons beneath Titan's dense atmosphere, compounds that, years later, led to the Cassini-Huygens mission. Meanwhile, Voyager 2 followed a different path. It didn't get to fly by Titan, but passed through Saturn's ring plane, observing other moons like Hyperion, Enceladus, and Tethys in detail. Its images revealed surprising geological features on those moons: ice structures, fissures, and signs of geothermal activity. Voyager 2 also got a better view of Saturn's delicate ring structure, uncovering even more complex and variable patterns than those seen by Voyager 1. These data helped scientists understand how the rings form and stay stable. With the first phase of the mission a success, Voyager 1 wrapped up its planetary tour after studying Titan. That close pass gave it such a strong gravitational boost that it was launched out of the planetary orbital plane and on toward interstellar space. Voyager 2, meanwhile, stuck to its planned trajectory, using Saturn's gravity to reach its next destination, Uranus. After leaving Saturn behind, it continued toward Uranus and, in 1986, became the first, and so far only, probe to visit that planet up close. The encounter revealed a world full of surprises. Uranus is a gas giant like Jupiter and Saturn, but with its own quirks. Its atmosphere is calm and serene, with no visible storms, very different from the turbulent giants. The average temperature drops to a staggering -223 degrees Celsius, making it one of the coldest bodies ever observed in the solar system. What really stood out, though, was the extreme tilt of Uranus's rotation axis, almost 90 degrees relative to its orbital plane. In other words, Uranus spins on its side, with its poles nearly pointing at the Sun. That means, over its 84-year orbit, each pole experiences long stretches of constant daylight and total darkness, an odd feature that completely changes how its atmosphere behaves. During its flyby of Uranus, Voyager 2 made more remarkable discoveries. It identified 11 new natural satellites, including moons with wildly varied surfaces. Miranda, for instance, showed a complex fractured landscape with deep canyons, cliffs, and formations that look like the result of a massive collision. Scientists believe Miranda might have been shattered by a colossal impact and then reassembled by its own gravity, a true cosmic puzzle. Voyager 2 also discovered a ring system around Uranus. Though fainter than Saturn's rings, they added another layer of complexity to the planet. The probe gathered valuable data on Uranus's atmospheric composition, the presence of methane gas, and hints about its internal structure. After Uranus, Voyager 2 headed for Neptune. In 1989, more than a decade after launch, it arrived at its final planetary target. Neptune turned out to be an incredibly dynamic world. Unlike the calm of Uranus, Neptune's atmosphere is wildly active, with winds exceeding 1,900 kilometers per hour and giant storms like the Great Dark Spot, a tempest comparable to Jupiter's Great Red Spot. During this leg of the mission, Voyager 2 also discovered 6 new moons. Triton, the largest, proved one of the most fascinating objects in the solar system. It orbits in a retrograde direction, meaning opposite Neptune's rotation, suggesting it was captured by Neptune's gravity. Triton's icy surface features polar caps and signs of geological activity, including frozen nitrogen geysers that blast material kilometers into the sky. Neptune also has rings, though dark and faint. Voyager 2 captured them in detail, sending back over 10,000 images during the mission. Once its Neptune flyby wrapped up, Voyager 2 said goodbye to its planetary mission and set off toward the edge of the solar system, just like its sister craft, Voyager 1. When the Voyager mission was first designed, the optimistic goal was simply to reach Jupiter. Voyager 2 was even slated as a backup in case Voyager 1 failed, but both far exceeded expectations, operating flawlessly for decades and providing historic observations of all 4 giant planets, revealing the solar system as never before. After completing their primary objectives, the probes were given a new mission, the Voyager Interstellar mission. This stage aimed to study the space beyond the heliosphere, the bubble carved out by the solar wind around our planetary system. But before venturing truly interstellar, another milestone awaited. In 1980, after Voyager 1's Saturn flyby, Carl Sagan suggested pointing the spacecraft back at Earth to snap one last photo from billions of kilometers away. Although Earth would appear too tiny for direct scientific value, the symbolic impact would be immense. Engineers worried that the Sun's position might damage the sensors, so the idea was delayed. Only in 1989, once the Interstellar mission began, did they proceed. In 1990, Voyager 1 captured a series of images of the solar system and the Sun, what came to be known as the family portrait. Among these was the now iconic pale blue dot, in which Earth appears as a tiny speck, almost lost in a ray of sunlight. That image became a symbol of cosmic humility, a reminder that everything we know, all our histories and loves, are contained on that singular point in the vastness of space. After that final photo, Voyager 1's cameras were shut off forever to conserve power. From then on, only the scientific instruments needed for the interstellar voyage remained active. Remarkably, both probes are still operational more than 45 years after launch. Voyager 1 officially left the solar system in 2013 when it crossed the heliopause, the boundary where solar influence fades and interstellar space begins. Voyager 2 reached that frontier in 2020. Today, they lie billions of kilometers from Earth, traveling in opposite directions, yet still able to communicate thanks to NASA's Deep Space Network, giant antennas in the US, Spain, and Australia. Each command takes about 23 hours to reach the spacecraft and another 23 hours for a reply. Communication is slow but effective. Over the years, non-essential instruments have been powered down to save energy, leaving only key sensors like particle detectors, magnetometers, and plasma wave instruments. In 2022, Voyager 1 puzzled scientists by sending garbled data. After weeks of investigation, they found the probe was transmitting information to an inactive computer, corrupting the data before it reached Earth. The issue was fixed, but its root cause remains mysterious. As of now, Voyager 1 is over 24 billion kilometers from Earth in uncharted space, carrying humanity's story on its golden record. Whether by technical glitch or some other factor, we may never know what caused its occasional odd behavior. What's certain is that it has traveled farther and lasted longer than anyone imagined. Estimates suggest communications with Voyager 1 will end this decade, around 2025. Voyager 2 may keep going until the mid-2030s, when its nuclear power source finally runs out. At that point, the probes will go silent and drift endlessly among the stars, each carrying a time capsule of images, sounds, and data from Earth. Perhaps another civilization will one day find them, or perhaps not, but they will remain. Silent reminders of our existence, our drive to understand the universe, and our capacity to dream. The Voyager journey stands as a testament to human ingenuity, science as a universal language, and our eternal quest for answers. Even if we never see them again, they continue on as silent ambassadors of our species, pushing the boundaries of what we know. If you've made it this far, thank you. And if you want to keep exploring the cosmos, subscribe to the channel. Because like the Voyagers, there's still so much more to discover on this journey toward infinity. See you in the next video.